So as we move forward now, on the schedule we have empirical and molecular formulas, so we'll go ahead and get started with that. All right, so we're on page 245. Now, with a lot of this, I think when we visualize all the problems that we go through, all the mathematical calculations, we look at it and we think, why is there a point to this? And that's probably a fairly decent question. This is probably one of the better ways that we can use this math for real world applications until we get to the stoichiometry. But one of the things we do try to determine the mass of a hydrate, which doesn't mean anything to you right now, because I think the last time we did that last year and the year before, it didn't work out too bad. But it's just the idea of trying to replicate this in a high school lab. It's just not very easy to do because there's a lot of things that can go wrong, okay? So nothing to where we're losing fingers or eyeballs or anything like that. We mean a lot of things can go wrong as far as, you could say, heating up your sample. You can overheat it, you can underheat it, which is better because you can always, let's say, when you are cooking something, is there something that you don't mind cooking? So eggs is a good example. Is it scrambled or over easy or
Scrambled.
Oh, see, now you're all fail. Okay.
Scrambled.
Yeah, it's easy, but see, I like to cook mine over easy. But the thing about that is, can you undercook eggs? Yes, you can. Is that bad? Yes. Not as good as your chicken example. That's probably even better. So when you're cooking your chicken, if you undercook it, you can just put it back in the oven, right? Or whatever it is you're cooking it in. So that's what I'm talking about when we're talking about a hydrate. So as we look out in the audience here, what does it mean to hydrate something?
You drink water.
Yeah, it's water. So what that means, if you're determining the formula of a hydrate, it's a compound that has water molecules mixed in with it. So you would boil that off. So it's just like if you didn't have it heated up long enough, you just do it a little longer, like your chicken. But you can overcook your chicken. So have you done that from experience?
Not me, but my parents have.
Yeah, I can cook anything, but I don't mess with chicken just because.
Well,
My dad's an overcooker.
overcooker, huh?
Yeah.
So what we're doing on page 245 is, just follow along. When a new substance is synthesized or discovered, it is analyzed quantitatively. Now, qualitatively would mean, okay, this is manganese, this is iron, this is cobalt. That's what we mean by qualitative. But quantitative then is how much of a substance, okay? To reveal its percentage composition. For these data, the empirical formula is then determined. An empirical formula consists of the symbols of the elements combined in a compound with subscripts showing the smallest whole number ratio of the different atoms in the compound. For an ionic compound, the formula is usually the compound's empirical formula. For the molecular compound, however, the empirical formula does not necessarily indicate the actual numbers of atoms present in each molecule. For example, the empirical formula for the gas dibromine is BH3, okay? But the molecular formula is B2H6. Were you thinking the same thing when you first read that? How can it be dibromine if it's BH3? There's no two boron. Did I say bromine? I did, didn't I?
Yeah.
Diboron, okay? You might be asking yourself, how can it be diboron if it's BH3? There's only one atom of boron in there. But that's the empirical formula. The correct way of looking at that is when you have to calculate the molecular formula, where you find two, and that's where they come up with B2H6. In this case, the number of atoms given by the molecular formula correctly or corresponds with the empirical ratio multiplied by 2. And that's something that you're going to be doing. We just have not applied that yet. To determine a compound's empirical formula from its percentage composition, begin by converting percent composition to mass compounds. Assume that you have a 100-gram sample. So that's one of the things that you do when we're talking about percent compositions. It's a molar mass problem, like where we would say if you had 300 grams of potassium nitrate, what's the percent composition of oxygen in those 300 grams of potassium nitrate? So you go through your steps and you find out, okay, there is, let's say, 110 grams of oxygen and 310 grams of potassium nitrate. So let's put that to words. Just for example, this is what we're talking about, what we've been doing. We say you have 300 grams of this entire substance. Well, what's the percent composition of just the oxygen in that 300 grams? So you go through your 4 steps and you come up with an answer, and maybe there's 110 grams of oxygen in 300 grams of potassium nitrate. So the percent composition would say you got to divide that by 300, and it's probably somewhere just like 32% or something like that. So these percentages then should add up to what then? 100. So that's where the 100-gram sample comes in, okay? Because it says assume, I'd rather say presume. Presume that you have a 100-gram sample of the compound, then calculate the amount of each element in the sample. For example, the percentage composition of diborane, diborane is 78% boron and 21.9% hydrogen. Therefore, 100 grams of the diborane contains 78 grams of boron and 22 grams of hydrogen. Next, the mass composition of each element is converted to composition in moles by dividing the appropriate molar mass. So if we have 78% grams or 78% of boron, we take the percentage, change it to grams. So then how do we change grams to moles for boron? So where did 10.81 come from? What did you just say correctly? Yeah, the atomic mass of boron is 10.81. So you are converting them to moles, and then what you do is you find the smallest whole number ratio, which you see, well, it's not 21.7, that's for hydrogen. 7.22 is a smaller number. You find the smallest number of moles and divide that into each substance. That will give you the empirical formula. These values give a mole ratio of 7.22 moles of boron to 21.7 moles of hydrogen. However, this is not a ratio of the smallest whole numbers. To find such a ratio, divide each number of moles by the smallest number in the existing ratio. So maybe we got a little bit ahead of ourselves, but that is what you're doing. Next page. Because of the rounding or experimental error, a compound's mole ratio sometimes consists of numbers close to the whole numbers instead of the exact whole numbers. In this case, the differences from the whole numbers may be ignored and the nearest whole number taken. Thus, therefore, contains atoms in the ratio of 1 to 3. The compound's empirical formula is BH3. Sometimes the mass composition is known instead of the percentage composition. To determine the empirical formula in this case, convert mass composition to composition in moles. A lot of this probably doesn't make any sense until we apply it. To calculate the smallest whole number ratio, the process shown in sample problem M. Okay, so you have these sample problems. I always say I just allow you to go ahead and read through those and do that on your time. But sometimes maybe it's a little too confusing. We can just hit the highlights in sample problem M. If you were to read that, it just says quantitative analysis shows a compound contains 32.38% sodium, 22.65% sulfur, and 44.99% oxygen. all those percentages are going to add up to what?
100.
Right, so there's your 100 gram sample. So that's why you see in the compute portion, instead of 32.38%, it says 32.38 grams. You do that for the sodium, the sulfur, and also the oxygen. And then notice it gives you a ratio in moles that you can't write that for the formula because it is not a whole number setting. You can't write Na 1.4, S 0.71, and oxygen 2.8, okay? You need to have whole numbers like Na2, maybe Cr5 and O7 or something like that. Okay. So there's sample problem M. I would allow you to read through that at your own time. Let's go ahead and look at, see, we're at 120 already. A compound is found and contains 63.52% iron and 36.48% sulfur. Find its empirical formula. So we know that those percentages are going to add up to, of course, 100. So you take that percentage and convert that to grams, which just means you're taking 63.52% iron is actually 63.52 grams of iron. Then the other one was what, 36.48 grams of oxygen. So one of the things throughout the course of this year, I would say about 90 to 95% of the time, see something that's measured in grams, you're probably going to convert it to what?
Moles.
You're probably going to convert it to moles. Because it is such a useful tool, because as we established, that mole ratio, it allows you to change what you have into what it is you're looking for. That's why changing it into moles is such a practical application. Yes?
Isn't it sulfur?
What did I say?
Oxygen?
Oh, I put oxygen there.
What are we on?
We're on sample problem 1 on page 247. Not sample, practice problem. Okay? So now, again, if we see it in grams, you're probably going to change it to moles. So, well, not probably, but 90+% of the time you'll probably do that. So how do we change this to moles of iron now?
Divided by the mass of itself.
Okay, so approximately 55.85 grams of iron will give you 1 mole of iron.
Yes, sir.
Okay, then for this, we would say for every 32 or 36.48 grams of sulfur, to get a mole of sulfur, you need 32 point.
Since it's in a percentage, wouldn't you have to put it behind 0?
7.
Okay, I need to process that question quick. So now moving forward, what this means here is we know this substance, maybe it gets put into a mass spectrometer or gas chromatograph, probably a mass spectrometer. You're taking a substance up with distilled water. You take that little syringe and you input that into the machine, and there's a laser that shoots through there, and how that diffracts, that laser will tell you what your composition is, probably what element and what the percentage is. So what this means is we know that this unknown substance, it has iron in it and it's got sulfur. Maybe that's the right formula for it. Maybe it is, maybe it isn't. Okay? So the first thing we need to do is go ahead and convert these to moles. And this is probably going to be pretty close to 1, correct?
Yes, 1.14.
1.14 moles of iron. Okay? Then for this one's probably pretty close to 1.
Yeah, 1.14 is
1 point, yeah, 1 point.
Okay? This one's fairly straightforward. We said once you convert it to moles, then you find the smallest number and then divide them into each other. Well, since these are the same, nothing's going to change. So does this compound exist as it's written right now?
Yeah.
Yes, because sulfur has a charge of negative what?
2.
And iron can have a charge of what?
+2.
And +3. But in this case, this is telling us that we don't have iron 3, we've got iron 2. Those charges add up to 0, so that's got to be right.
Can we do another one?
Sure. 2 or 3?
2.
Okay?
Wait, actually 3. Can we do 3?
Well, 2 is a little longer,
Okay,
but
let's do 2 then.
okay. All right.
I was just trying to figure out which one was hardest.
Find the empirical formula, this is number 2, of a compound found to contain approximately 26% potassium, 35% chromium, and then the remainder oxygen. You're going to see a lot of problems that are going to be worded that way.
So we add
Because-
those up, leave it the other thing.
Exactly. That's why you have to make those presumptions that it is a 100-gram sample, because you get that from the percentages. That is correct. Okay. I just erased the whole thing. That'll probably be easier. So we know that this mass spectrometer spit out this substance. We know that there's potassium in there. We know that there's chromium in there. And we know there's oxygen. Maybe this is the right formula, just like it was up here. Maybe it's not. Okay? So to start this out, okay, what was the percentage of potassium? It was 30 something, right?
26.5.
26. Now that was a percentage, but you take that percentage and you change that to grams. Okay? Then what is the chromium?
35.41.
And then notice it said the rest is then oxygen. Well, we're not just pulling that number out of the air, like you correctly said. You would add these two numbers together and subtract from 100, and that gives you what?
38.02.
That's grams of oxygen. Okay. So the next thing you're going to do is go ahead and convert these to moles, and then we'll go ahead and come back to that. Just gives you a little more practice. Okay, so we gave the students a little bit of time to work on this. Excuse me. Is there anything here that is not right? Is this the atomic mass for potassium? I don't have a table in front of me.
Yeah.
Is this right for chromium?
I got 52.
Oh, okay. It's right at 52. It's not 52 point, because there's one of those elements in the.
1.99.
Okay, so yeah, so it's 52. I knew there's an element in that D block that comes out evenly, and of course oxygen 16. So then what you're going to do is convert them to moles. And who's got the moles of potassium?
0.68.
And 68, okay. So if this doesn't work out, sometimes what you might want to do is extend some of these decimal places out. But we can try this, moles of potassium. So what do we get for the chromium?
0.68.
Okay, it looks like we're heading to 1 to 1 to 1 again.
Uh-oh.
And then you have 2.38.
Well, there went that theory. It's not going to be 1 to 1 to 1. Okay, you said 2.38 moles of oxygen. So this is not our correct whole number ratio. We can't write potassium 0.68. We can't write chromium 0.68 and then oxygen 2.38. What's your next step? You find the smallest one,
Subtract it.
and you don't subtract, you divide. So then I can do this division and this one. I don't even need a calculator for that. Yeah. Okay, so this would be 1 to 1, and where that number comes from, we said find the smallest one. So that's going to give you 1. It would do the same thing here. So we're getting closer, But what happens when you divide 2.38 by 0.68? And then notice we can't write this as 1 to 1 to 3.50. That's not a whole number or even whole number. We would not round it. We're going to multiply it.
5.50.
What?
So, for instance, if, and I don't know why this would come up, but maybe people want to get rid of their currency. You're at the concession stand and, okay, something costs $3.50. Well, I want to get rid of all of this. So they give you $7. I don't know why. We're just using that as an example. Here's $7. How much change do they get?
Nothing.
You get $3.50 back again. Okay? So the point is you're taking that $3.50 times what?
2.
What happens if you multiply that by 2? You're going to get a nice round number of 7. But you don't just do it to this one. You have to do it to all of them. So therefore, we've got 2 potassiums, 2 chromiums, and how many oxygens? So that's what we mean in this process. You take your percentages, change them to grams. Once you have them in grams, change them to moles.
So then that end up being 200% of it, right? Because you know how we normally go to 100?
I don't think you're kind of going into the weeds there if you are going sideways if you say this is 200. I'm sure there's a more logical explanation than that, but
Well, you know
I
what
don't
I mean,
have.
like-
I do know what you mean because what we're saying is we're starting with 100 and then we double this. Does that mean there's 200? I don't think so. Yes.
How'd you get the 350 again?
Okay.
You subtracted.
Nope.
Divide.
If you take 2.38 divided by 0.68, it gives you 3.5.
And then you
Alright.
always, so if it's not 1 to 1 to 1, you always multiply the odd one out or all of them by 2.
Right.
Or
So
it's a constant.
it could be 2.5. It could even be 0.50.
Okay.
Okay. It could be even 7.5.
But like no matter what, whatever like the odd ones come out to. So let's say like the chromium one came out to a different number too.
Okay.
And it was just like 0.68 was the smallest. Then you'd multiply the chromium and the, like, it'd be 2 different separate ones
Correct.
by 2 every time.
So that's correct. But sometimes the smallest one might come out to, and this will happen in here. What happens if you get 3.32? You would multiply it by 3 because you're on a third. This is on a half, you double it. If it's on a third, you don't double it, you triple it. And then if it ends up on a quarter, you quadruple it. Okay? So that way, if you multiply this by 4 then, doesn't that give you 5? Okay? You multiply this by 3, okay? That would give you approximately 9. And then of course you double these. Okay.
I just don't understand how, so when I.
Well, we just haven't spent a lot of time on it yet, so that's possible. Yes?
I divided 38.03 by 16 and I got 2.38.
Right. That's what we got down here too.
How did that go up to 350 then?
You took
You're
the
dividing it
by
by 0.68.
You find the smallest number on the moles and divide them into each other. It's just that when you did it here, so that's why I said I can do this math because it comes out to 1. But this one, I said, well, I need a calculator for that. Okay, so we will continue with these molecular. We might get into molecular formulas tomorrow. There's another example we can go over. Then it does have molecular formulas on the next page. All right, so we will catch up to you next time.